It is difficult to represent it on a flat surface. To do so, it has to be projected. There are many types of projection, but the one most commonly used at sea is called the Mercator projection. It projects the sphere onto a cylinder. Because the resulting distances between the latitudes is constantly increasing, it is called a progressive projection. The advantage of the Mercator projection is that longitudes and latitudes are at right angles, and it makes it easy to read true bearings. At small scale, the Mercator chart also gives true distances. Unfortunately, because distances in longitudes are equal to the cosine of the latitude, the Mercator projection cannot really be used near the poles, where distortion reaches its maximum. As an example, a Mercator projection at latitude 60 degrees north gives a 1 by 1 degree rectangle, which is twice as high as wide, the cosine of 60 degrees being 0.5. Small-scale charts are always based on a Mercator projection. The nautical mile is by definition 1 minute of a degree of latitude. 1 degree is traditionally divided into 60 minutes, with each minute divided into 60 seconds. Today, however, nearly all nautical charts and navigation instruments indicate degrees, minutes and tenths, or hundredths of a minute. 1/100th of a minute of latitude corresponds to 18.52 meters, and this exceeds the accuracy of most navigation systems or charts resolution. Dead reckoning is obtained by measuring the distance covered since the last position was noted, and drawing as an equivalent line in the direction sailed. Note that on a Mercator chart, distances always have to be measured from the nearest latitude scale, as it varies for each latitude. The Earth is not a perfect sphere. This wasn't a problem until satellite navigation systems started to give positions in 3 dimensions. To do this, the calculation assumes a perfect sphere and corrects the elevation at the actual place of observation. This correction is called the geo-idle height. Charts are relatively accurate, but they were drawn long before the satellite surveys were available. In order to correct charts to the extreme accuracy of satellite positioning, a standard reference had to be created. The World Geodetic System of 1972, superseded in 1984, is the reference datum charts should be corrected for when reading satellite system position. Usually, charts will indicate the north-south and east-west correction to be added in order to conform to the World Geodetic System datum. The position of a vessel is found by plotting lines of position on a chart. These are found by dead reckoning, taking bearings, or by reading navigation instruments. A line of position is a single line drawn from a single measurement. It can be from the observation of a celestial body, or a bearing from a landmark, or a radio navigation instrument bearing. A minimum of 2 lines of position are necessary in order to assume a position. Usually, 3 lines of position are used, and the position is assumed to be inside the triangle, or cocked hat, created by the intersection of these lines. Note that if lines of position from celestial observations are in fact curved lines, at a small scale they can all be drawn as straight lines. A vessel is said to sail on a course. However, one must differentiate between the direction in which the vessel is pointing, the heading, and the direction in which the vessel is travelling relative to land, the ground track. The difference is the result of the combined action of the tidal stream, currents, and wind speed, and is called the drift or leeway. Plotting the dead reckoning position requires the plotting of a vector based on the heading and the distance sailed through the water, followed by the plotting of a vector of the drift. The resultant of the two vectors is the estimated dead reckoning position. Today, all electronic navigation instruments give the calculated position in degrees of latitude and longitude. To plot the position is a simple matter of drawing the intersection of the given latitude and longitude. Chart work is best done with a pencil and a slide ruler or parallel rulers. When the position is plotted, the following notation is made: the time, usually UTC time, the log counter reading, and eventually the words fix or DR to denote if the position was obtained from an instrument reading or from dead reckoning. With time, in which direction, and at what speed a vessel is moving. Most radio navigation instruments and some Doppler sounders will compute the course and speed of a vessel over land, but a vessel of any size relies on the compass and the log to find the direction and speed through water. Logs measure the speed of the vessel. They can be divided into two categories. The first measures the speed through the water, and the second the speed over the ground. Older logs work using a rotor or impeller, the speed of which is registered by the distance log and the speed log. These mechanical logs are subject to marine fouling and are not very reliable. Other logs measure the change of pressure in a tube, or the change in the electromagnetic field as water passes along the hull. The Doppler log measures the speed over the ground by measuring the Doppler effect from the return of a hydroacoustic signal. It doesn't give an accurate reading in deep water or very shallow water. It is essential to understand that if the Doppler log gives the speed over the ground, it is only to be used for navigating to a destination. Collision avoidance maneuvers shall only refer to the speed through the water. The difference between the latter and speed over the ground is the combined effect of currents, tidal streams, wind speed, or possible instrument error. Ultimately, the navigator wants to know his speed made good, which is the speed toward a destination or a waypoint, in order to find his estimated time of arrival. The magnetic compass is compulsory on every vessel. As it is prone to error due to the proximity of steel constructions and magnetic distortion, a deviation correction is used. Furthermore, its reading has to be corrected for magnetic variation in order to find the true bearing or course relative to the geographical north. The magnetic compass is always placed outside steel constructions and is calibrated to compensate for local magnetic distortion. The gyrocompass is mechanically based on a gyroscope set to the true north. The latitude and the vessel's motion influence its initiation. Therefore, it has to be started in good time before the beginning of a journey and must not be stopped whilst underway. It is important to check the gyrocompass at the beginning of each watch and whenever speed has been changed. The returning echo is displayed on recording paper, on a monitor, or simply on a digital meter. The two former have the advantage of showing the signal strength and an indication of the nature of the seabed. A hard, rocky seabed will show as a bold line. A soft muddy bottom will show as a diffuse line. On a monitor, different colours indicate the strength of the signal. Apart from the sea bottom, a recording echo sounder will also display echoes of schools of fish, and even single large fish. Sometimes a false bottom echo appears. This is called a scattering layer, and it is the result of reflection between two layers of water with different density or temperature. This often happens at a river estuary, where a layer of fresh water lies on the top of denser, salty water. The first radio navigation aid was the radio direction finder. A land-based transmitter sends a Morse-coded radio signal on the long wavebands, and an onboard receiver equipped with a directional antenna takes a bearing on the signal. Two or more bearings on several radio direction finder stations give a cocked hat position. Maritime stations are often placed at lighthouse locations and work in sequence on the same frequency. This allows the navigator to take cross bearings without having to switch between frequencies. Aeronautical radio direction finder stations near the coast can also be used for maritime navigation. Low-frequency radio direction finder signals are bent by land masses, and therefore care should be taken when the signals received make a small angle with the coastline. The Decca system was British and covered most of Europe. It was based on a hyperbolic line of position principle. A master radio station sent a signal that was received by 2 or 3 slave stations. The slave stations then sent a signal which, when received by the on-board radio instrument, was compared to the master signal, and the time difference was converted into 2 or 3 hyperbolic lines of position. The Decca Navigator system was discontinued in 2000 after half a century of good service. The Loran-C system also uses hyperbolic lines of position, but it works in a different frequency range and has a larger range. The Loran-C is a US Department of Defense system and covers the United States and parts of Europe. The Omega system works on low-frequency signals from 5 worldwide transmitters. The system is based on range finding from signal time delay, being synchronized by an atomic clock. Omega is also maintained by the US Department of Defense. The Transit satellite was the oldest satellite-based navigation system, but it is no longer in operation. Today's Global Positioning System is the most advanced and accurate navigation system available to seafarers. These satellites are high in orbit, thus allowing for several signals to be computed simultaneously by the receiver. The position accuracy is in the range of a few meters. However, since the US Department of Defense wished to keep a strategic edge over other military nations, the civilian version of the GPS had an induced error factor called the selective availability, which at times could induce several hundred meters of position error. The selective availability was removed in 2000, hopefully for always. Sometimes too few satellites are available within the favorable angle over the horizon. In that case, an error called bad geometry or dilution of precision arises, and the calculated position may become unreliable. Depending on the receiver setting, it may decide to stop calculating the position entirely until the satellites are in a better geometry. The newer differential GPS system receives, in addition to the satellite signals, a correction factor from a land-based station. Its accuracy is within a very few meters. Without doubt, the radar is a highly important navigation aid. If it is intended for collision avoidance, the radar is also a good help in identifying coastline and buoyage in any weather conditions, day or night. Its range reading is more accurate than its bearing reading. However, a low-lying coastline with a long, flat beach will show up poorly on the radar. This is a potential hazard, as the radar may only show high features far away inland and give the impression that the coast is more distant than it is. The Raycon is a radar transponder often installed on major waypoint sea marks. It is also often used on sea marks indicating the beginning or crossing of a traffic separation scheme. When activated by a radar signal, the Raycon sends it back with an identifier. It may be a short Morse code, such as the letter E, T, A, or N. Digital charts, either presented on a plotter or an ECDIS, have the advantage of being easier to read because information is organized in layers, which can be displayed or hidden. Usually, the digital chart will display the vessel's position from a GPS or differential GPS receiver. Advanced ECDIS technology can display the digital chart and the radar picture at the same time. Often the digital chart is overlaying the radar, and the water area is kept transparent in order to show the moving targets and sea marks. Lighthouse Authority's buoyage system. The International Association of Lighthouse Authorities buoyage system is divided into two categories: the lateral system and the cardinal system. The lateral system is used in restricted waters, such as buoyed channels. In Region A, which includes all of Europe, the green buoys are kept to starboard and red to port when sailing from sea to land. In Region B, it is the opposite. The cardinal system refers to the geographic four quadrants north, south, east and west. This system is used to mark navigational hazards, such as shoals, reefs or wrecks. Different black and yellow stripes and different cone shapes identify the four cardinal marks. In addition, there are a few buoys for marking standalone dangers, such as wrecks or working areas in buoyed channels. In confined waters, traffic separation schemes ensure safe navigation as it separates inbound and outbound traffic in well-marked lanes. Regulations request all vessels to join or leave these lanes at their extremities. If impractical, the lane should be entered at as shallow an angle as possible. If a traffic separation scheme has to be crossed, it has to be carried out as close as possible to a right angle. Being in the traffic separation scheme doesn't change the general rule of the road convention. Vessel traffic services can be expected at traffic separation scheme areas and at port approaches. Reporting is often compulsory. Traffic control is called on its working VHF frequency. Even if reporting is not compulsory, a sharp watch on VHF channel 16 is to be kept. Unsafe navigation in restricted water or in a traffic separation scheme will most likely be noticed, and the navigator should follow the instructions of the Vessel Traffic Services Center. The straight line drawn between 2 points is called the rhumb line, or loxodromic line. On a sphere, the shortest distance between 2 points is the great circle passing through these points. All the longitudes and the equator are great circles. That is, they divide the sphere in two. Navigating along the north-south axis or along the equator is simply a matter of following the bearing to the destination. Navigating to any other distant destination requires the calculation of the Great Circle Line. If both points are on the same hemisphere, the Great Circle Line will always be closer to the pole than the rhumb line. The Great Circle Line can be found by using trigonometry, special Great Circle or mnemonic charts, passage pilot books, or nowadays on the onboard navigation computer. When using the mnemonic chart, the navigator draws a straight line between the points, then notes the latitude for every 5 or 10 degrees of longitude, and transports it to a Mercator chart. In practice, the most favourable route will be calculated taking in account other factors such as the weather pattern, ocean currents, drift ice and land masses. Ocean weather forecasts are available from different radio sources. Coastal radio stations transmit the forecast for different areas on the short wave bands. WeatherFax, or WeFax, can also be obtained in some areas. Lately, weather information can also be obtained via Inmarsat and Navtex. Usually, a gale warning is issued when the average wind speed can be expected to reach or exceed Beaufort Force 8. A storm warning is issued at Force 10. Meteorology is the science of registering and forecasting the weather. Extreme weather conditions are still a potential danger to shipping. Detailed shipping forecasts is given for most sea areas. It usually gives the wind direction, strength, sea state, and visibility. The planning of a deep-sea voyage taking account of the weather is best done by using weather maps with isobar lines. These are lines of equal atmospheric pressure. At a glance, the navigator can see where the lines are steep and where he can expect the worst weather. Winds always blow from a high pressure to a low. Tight isobar lines always indicate strong winds. The barograph is still an important instrument on board. A steep fall or a steep rise in the pressure always warns of gale-force winds. In temperate regions, lows usually move eastward at an average speed of 20 knots. In equatorial regions, lows usually move westward. On a long-distance passage, the cautious navigator will monitor the weather pattern and periodically alter course and speed in order to avoid the worst conditions. Is the means of finding one or several lines of position using a sextant, a chronometer, a celestial almanac, and conversion tables. The methods of finding a position using celestial bodies are numerous and beyond the scope of this training module. We will merely introduce some elementary notions. The celestial bodies that can be used for navigation are the pole star, the Sun, the Moon, Jupiter, Venus, Mercury, and some other designated stars. The Sun has the advantage of being visible during daytime. At night, it is often difficult to sight the horizon. A full moon, low over the horizon, will give a good sight, so will Venus, which is often visible before sunset. Mercury is often too close to the Sun in order to be sighted, but the Moon and the planet's trajectory is complex, and finding a line of position requires a lot of calculation. The sextant is a fragile instrument that has to be calibrated properly. An error of 1 degree of latitude represents 60 nautical miles on the chart. An index error should be plotted by calibration and added to the calculated elevation. Whilst nowadays radio time signals can be received anywhere on the ocean, it is worth mentioning that chronometer error of 1 minute would give, at the equator, an error of 15 nautical miles on the chart. To find a celestial body elevation with the sextant, it has to be first set to the estimated degree of elevation. Then, while holding it firmly, adjust the vernier screw until the observed body kisses the horizon. To make sure that the sextant is kept in the vertical plane, the navigator should slightly swing the sextant as a pendulum and read the shortest value. The latitude is easiest found by observing the pole star, or the Sun, when it is at its meridian. The elevation of the pole star above the horizon translates roughly into the latitude. To find an accurate latitude, a set of corrections has to be computed. This includes the correction for the time of day and year, the correction for the refraction dip, and the correction for the observer's height above the water. Note that the pole star is best observed between latitudes 10 degrees north and 60 degrees north, where it is easy to take its elevation. However, it is not visible in the southern hemisphere. Finding the latitude by observing the Sun requires measuring its elevation at its meridian passage. The Sun moves along an apparent circle above the horizon. When it is at its apogee, it is due true south and at its meridian. Sighting the Sun's meridian requires sighting the Sun some time before its assumed meridian time. Then, as it still rises in relation to the horizon, the vernier screw is adjusted until the Sun stops rising. The latitude is then obtained by subtracting the elevation from 90 degrees and adding the Sun's declination if it is in the same hemisphere in summer, or subtracting the declination if it is in the other hemisphere in winter. The observer's elevation, refraction, and half-diameter corrections also have to be added. In practice, all these are calculated before the time of meridian, and the elevation read on the sextant is subtracted, thus quickly giving the latitude. Finding the longitude is finding the distance from a reference meridian, like the Greenwich meridian. A simple method would be to find the local time of the Sun's meridian and subtract it from the Greenwich Mean Time. The Sun moves 360 degrees in 24 hours, which is a quarter of a nautical mile per minute at the equator. This time difference could then be translated into degrees of longitude. However, as previously mentioned, the time of the Sun's meridian can seldom be found accurately, because the Sun's apparent rise above the horizon seems to stop for several minutes as it reaches the meridian. The most common technique of finding the longitude requires taking a Sun elevation early in the morning, or late in the evening, when the Sun bears due east or west. Then a line of position, which is almost parallel with the longitude, is drawn. When this method is used, the noon position is integrated to the morning-evening position by recording the distance and heading between the two observations. The technique is similar to the running fix. Knowing the approximate latitude and the Sun's declination, it is possible to find the Sun's azimuth from the almanac. This is done when the Sun is half its diameter above the horizon. Taking a bearing on the Sun and comparing it with its calculated azimuth enables compass verification. Have red light to port, green to starboard, white astern, and 2 masthead lights. Unfortunately, vessels with many deck lights, such as ferries, make identification of navigation lights difficult. The two masthead lights are by far a better way to estimate the vessel's heading. An old thumb rule says, red on red or green on green is probably safe. Red on green or green on red is a potential danger. This is because observing a red portside light on your port side means that the vessel is probably on a reciprocal course. If the red portside light is observed on your starboard side, then the other vessel is most likely to cross your track. Fishing vessels, tugboats and other vessels restricted in their ability to maneuver will all display special lights. They should all be given a wide berth. Even when the vessel is equipped with digital charts showing its GPS position, it is a navigator's comfort to sight a lighthouse at its correct anticipated position. The skill of reading the light's identification characteristics is easy and should be practiced regardless of the other navigation aids available. A typical landfall at night would be like this. A powerful lighthouse with long range would be the first light sighted. This light would probably be an occulting or isophase white light. Later, a strong light, maybe placed on a platform, would indicate the beginning of a buoyed channel. Later on, one or several sets of leading lights would indicate the direction of a buoyed channel. Each of these buoys has a red or green light indicating the channel's navigable limits. Groups of these buoys would typically flash quickly or very quickly in sequences in order to distinguish them. Finally, a red and a green flashing light on the extremities of the harbour's sea walls would mark its entrance. The International Port Traffic Signals Convention is a set of red, green and white lights displayed in vertical sets by the port authorities and signalling if the traffic is allowed to enter or leave the port. These signals may also be used at locks and bridges. In cases when VHF radio communication cannot be achieved, the use of an Aldis lamp is still recommended. It can be used to communicate with port controls or other vessels. By using the International Code of Signals or the International Q Code, simple messages such as requesting the permission to proceed can be communicated. The sun influenced the water masses on the globe. The effect is termed semi-diurnal, which means that it happens twice a day. In confined waters, where it can move in a cyclic period, the tide will have a large amplitude. In other places, its effect will barely be noticeable. The tide is calculated from 5 basic astronomical speeds that consist of many constituents, which, added together, determine the total amplitude above the mean level of the sea at a given place. The range of the tide is twice its amplitude. The tidal height is usually the height of water above the lowest astronomical tide, which is called the chart datum. Nautical almanacs show the time of high water, low water, and tidal height for high water and low water at standard ports for every day of the year. When the moon and the sun are on the same or opposite side, their effect is stronger, and spring water occurs. This is usually a couple of days after the full moon, or the new moon. At the first and last quarter, the tide is the weakest. and it is called neap water. Finding the tide at a given place requires reading the time of the nearest high water or low water for that place. If it isn't a standard port, a list of secondary ports is given with a time difference and tidal height difference from the reference standard port. Tide calculation is often required in order to find the under-keel clearance at a certain place. To do this, the tidal height has to be found at the estimated time of arrival to that place. When the difference between estimated time of arrival and time of high water or low water is calculated, it can be plotted on a special tidal curve diagram found in nautical almanacs, and the tidal height at the estimated time of arrival can be found. It is then added to the sounding read from the chart, which is in most cases the chart datum. Note that strong winds and atmospheric pressure can change the amplitude of the tide and the time of low water or high water. Safe navigation will always include a margin of security under the keel. If no tidal curve exists, an easy thumb rule is the 12ths rule, which is an approximation of a sinusoid representing the tidal curve in open water. To find the tidal height at sea, the navigator can use so-called special co-tidal charts. They display lines of co-tidal time difference with the time of the moon's meridian and lines of equal tidal range. As the tide makes the water rise and fall twice a day, a resulting current or tidal stream is generated. The stream follows the tide and reverses accordingly. The tidal stream is strong where the tidal range is important, and it increases in narrow channels and near outstanding capes. Nautical charts indicate reference points where the tidal stream direction is indicated along with its rate, or speed, for mean spring water and mean neap water. Note that maritime convention is to indicate wind direction as where it comes from, but current or stream direction as where it goes. In river estuaries and enclosed waters, the tidal stream will often run seaward as the tide ebbs or goes down, but at other places it will simply follow the coastline. In river estuaries, the tidal stream may be combined with the water output from the river. In this case, the ebbing tide will be stronger and last longer than the rising tide. When reversing, the tidal stream will have a period with little or no effect. This is called the slack. Are now a part of GMDSS. Any commercial vessel still has the duty to listen to the maritime VHF channel 16 and MF 2182 kHz if installed. No radio equipment should be used without the presence of a licensed radio operator, but in case of emergency, any action may be taken. The maritime VHF is used for ship-to-ship and ship-to-shore communications. It is monitored by shore stations such as coast stations, coast guards, rescue, lifeboat stations, pilot stations, harbour authorities, and vessel traffic services. Typically, coast stations will announce Notice to Mariners and Weather Report on Channel 16, but will transmit it on a working channel. Ships can call other ships on Channel 16, but should move to a working channel as soon as possible. Apart from the Coast Guards, not all coast stations listen to Channel 16. Their working channel can be found in the list of coast stations. The proper procedure is to wait and see if the frequency is not already used. Call by stating the station's name or call sign, then your vessel's name or call sign, and the channel you are calling on. Be prepared to give your call sign in the International Phonetic Alphabet, your position, course and speed, and the nature of your traffic. VTS may call you and ask, in addition, the nature of your cargo and your port of destination.
The vessel heading 89 degrees at 40 knots. This is Greenet Control.
Greaseness Control, this is bulk carrier Aurora.
Aurora, channel 13, 13 please.
Channel 13.
Aurora, this is Greenet Control. Good evening, sir. May I ask your call sign, please?
Good evening, sir. This is the Norwegian bulk carrier Aurora. I spell it Alpha Uniform Romeo Oscar Romeo Alpha. Call sign Lima Kilo Alpha Bravo.
Thank you, Aurora. May I know your cargo and destination, sir?
My cargo is iron ore and we are bound for Rotterdam.
Thank you for your cooperation. Have a pleasant journey, sir. Aurora, Greenet Control out.
Thank you. Have a nice watch, Grease Control. Aurora, back to channel 16.
In busy waterways, the traffic evolves mostly without problems, following the rule of the road and eventual traffic separation schemes. Sometimes, at certain waypoints, the intention of another vessel may not be clear. If in doubt, call the vessel and ask for his intention. You do that by calling on channel 16, stating the vessel type, course and speed, and inviting him to answer on a ship-to-ship channel, such as channel 06. If the action is of extreme urgency or several vessels are involved, you may stay on channel 16.
Supply ship heading northwest at 12 knots. This is the bulk carrier Aurora on your port side. Channel 6, please.
Aurora, this is Kansi 2, channel 6.
Kansi 2, Aurora. Good morning, sir. What's your intention?
Well, sir, I'll keep my heading, but will increase speed. I think you'll pass safely to my stern.
Okay, Kansi 2, this is just fine. Have a nice trip, Kansi 2, Aurora out.
Thank you, sir, and a safe passage to you. Kansi 2 out and back to 16.
If you ever hear silence mayday or silence distress on any frequency, unless you are directly involved in the action, you are to remain silent on this frequency until a distress finie is sent by a rescuing authority.